I am going to talk about novel phases in SUN designer Hamiltonians with two-column representation. And this work was done in collaboration with Shauvik Kundu, who is a PhD student, and Professor Kedar Damle at TIFR. So I'll start by describing the kind of models we study. So we use quantum Monte Carlo methods for our simulations, and as is well known that these models suffer from the infamous sign problem. So in brief, when we do a mapping from a quantum problem to a classical statistical mechanics ensemble, which we want to simulate on a computer, if there's no way of going from the quantum problem to the classical problem, that is, there's no basis, there's no known basis, where all the weights in this ensemble are non-negative, then we say that we have a sign problem. So what are the models that we can simulate? So one model that's known to be sign problem free is the nearest neighbor antiferromagnetic Heisenberg model on a bipartite lattice. And it's known to realize the ground state, which is the antiferromagnetic nail state. And now, how do I realize a phase transition out of this magnetically ordered state at zero temperature with a model that I can simulate with QMC? So that's where designer Hamiltonians come in. So designer spin Hamiltonians are those models that are constructed to not have a sign problem when I simulate with QMC methods. And apart from not having a sign problem, they also host some interesting ground states, which you can find in other systems that might not be sign problem free, like, for example, geometrically frustrated systems. So it's desirable to study these designer spin Hamiltonians, which host interesting ground states and also are amenable to large scale quantum Monte Carlo simulations. So how do we introduce quantum fluctuations? One way is to increase the symmetry of the model from SU2 to SUN. So the spin half Heisenberg model is SU2 symmetric, and on a bipartite lattice, I can carry out a unitary transformation on one of the sublattices, say the yellow sites here. And I can show that I can write this model as a sum on singlet projectors on nearest neighbor bonds. And the singlet is an SUN singlet, which is given like this. So the spin states at each site are in the fundamental representation of SUN on one of the sublattices, say the A sublattices, and the conjugate to fundamental on the other sublattice. So what happens here when I increase the value of n, that is, I'm increasing the quantum fluctuation. So for n equals 2, I have the nail phase. And for n greater than or equal to 5, it was shown using theoretical large N expansion methods and numerical methods that it realizes the valence bond solid phase for n greater than or equal to 5. So this is one way to increase the quantum fluctuations. The other way is to introduce some competing interaction that destabilizes nail order. So this is one simple sign problem free model that is widely used. So here, this is a multiplication of the singlet projection operator on two parallel bonds on a plaquette in both directions. And if you sum this over all elementary plaquettes of the square lattice, it realizes the VBS phase on the square lattice. So this has been extensively studied owing to the great interest in studying the nail VBS phase transition, which is an exotic phase transition. And these are just a small subset of numerical works that study this, that use this designer Hamiltonian to study this phase transition. And so these spin half models and their SUN generalizations have been studied extensively. And what we want to do is we want to increase the representation, go to a higher representation and look for some more interesting phases and phase transitions. So let's go to the spin 1 case. So in the 1D chain, we already know there's a very interesting phase, which we call the Haldane phase. So we understand this by writing each of the spin 1 sites as two spin halves, and each of the spin half forms a singlet with a neighboring spin half, and that explains the disorder in the system and the spin half edge modes. And this construction was given by Affleck, Kennedy, Lieb, and Tasaki. So as we can see here that this representation of a spin S in terms of spin halves, which I call mini spins, is extremely helpful in understanding what phase we have here. There are other advantages which we find. One of the most important advantages is that it makes efficient simulations of spin S models possible. So you can write each of the spin S as in terms of 2s spin halves, put a symmetrization operator to make sure that all the spin halves are symmetric, and simulate any arbitrary spin S model in quantum Monte Carlo. And this was realized by Todo and Kato. We can also write down designer Hamiltonians, that's sign problem-free Hamiltonians, for arbitrary spin S using this mini spin representation. And that was some of my previous work. Another very important advantage is that this language renders it easily generalizable to SUN. And we're going to take advantage of that. So I'll explain what the two-column representation is in this mini spin language. So here I have two SUN sites, and at each site I have two mini spins, and I have a singlet projection operator between two of the mini spins. Now I can put this operator between any two of these mini spins, and I have 4 possible interactions, and I can sum all of them. And I want to make sure that in all my eigenstates, these two, each mini spin appears completely symmetrically. So I put a local symmetrization operator at each site. That's the P1 and P2. So now this Hamiltonian is equivalent to the Heisenberg Hamiltonian. So if I take n equals 2 here, it's equivalent to the spin 1 Heisenberg Hamiltonian up to a unitary transformation on one of the sites. And in general, in Young tableau language, the spin states on one site are in the representation with 1 row and 2 columns. And on the other sides, it's in the conjugate representation. So I can simulate this nearest neighbor model on a bipartite lattice, where one sublattice of the bipartition is in one representation and the other sublattice is in the other representation. So when I increase n in this model, I get an interesting phase. So this phase is one that breaks the rotational symmetry of the square lattice. So so this was shown using theoretical results again and numerical simulations. And this phase consists of Haldane chains in either the x direction or the y direction. And so now I can also introduce a competing interaction that destabilizes Snail order. And this is one new designer interaction that we introduced. So here I have a singlet projection operator. Here I have 4 spins, and each site has 2 mini spins, and I have a singlet projection operator between the mini spins on 2 neighboring sites, and these form a ring. And this, on a square lattice, realizes the plaquette valence bond solid phase, which looks something like this. This phase only breaks the translational symmetry of the square lattice in the x and the y direction, and it's a 4-fold degenerate phase. While the phase I showed before, the Haldane nematic breaks only the rotational symmetry. So now I can study a phase transition between 2 phases by varying q over j in the Hamiltonian. And so what I'm going to present here is this large n phase transition, where I study a phase transition between these 2 phases, ordered phases, one which breaks the rotational symmetry and the other which breaks only a translational symmetry. So before I show the results, I'm just introducing the order parameters. So the order parameter for the nematic phase is, I call it psi. It measures the number of bonds in the x direction and subtracts the number of bonds in the y direction. And the order parameter of the valence bond solid phase looks for translational symmetry breaking along the x and the y directions. So if I break translational symmetry along both x and y directions, then that is the plaquette valence bond solid phase. If it's only in one direction, then it's a columnar phase. So if I have a joint histogram of phi x and phi y, which respectively measure translational symmetry breaking in x and y directions, If I have peaks along the axis here, I know it's a columnar order that I'm forming. And if I have peaks here, it is a plaquette valence bond solid order. So here are my QMC results. So I'm plotting the susceptibility normalized in such a way that it goes to a finite value in the thermodynamic limit if I am in the ordered phase. So on the left side, it shows that the susceptibility of the nematic order is going to a finite value. And this is for a small range of Q over J, where the nematic order starts to go away, but the VBS order has not picked up yet. And so what surprises us here are the huge error bars on the data, and which we usually see only when we are close to a phase transition. So I look at the nematic order parameter as a function of our Monte Carlo time, and I see it flip between positive and negative values, which is what I would expect if the ordering is going between the X direction and the Y direction in the nematic. But then it also goes to 0, indicating disorder, and that puzzles us because we are at a very low temperature. These are the lowest temperatures we have simulated. And so when we compare this for two different system size at this is at in the 0 temperature limit, and we find that the peak at 0 psi squared just gets sharper and sharper as I increase the system size. So it survives in this thermodynamic limit and in the low temperature limit. So this indicates that we have some sort of a coexistence of the nematic phase with the disordered phase. And then when I look at the VBS order parameter, it just peaks at 0. So there's no VBS phase here as expected. So this suggests that we have a proximate spin liquid where we have some sort of a coexistence between a nematic phase and a disordered phase. And if I increase some coupling, I might go into a spin liquid phase. And so I increase the value of Q over J even further. And what I see is the nematic order starts getting suppressed, but this peak remains. So there is a small sliver where this proximate spin liquid survives. And so then I go into an intermediate phase of Q over J, where the susceptibilities of both nematic and VBS go to 0. So this is a phase where I have neither order, neither nematic nor VBS order. So this is our candidate for a spin liquid. And when I increase Q by J further, that's where the VBS order starts to pick up and the nematic order is 0. And so we make histograms of our order parameter here, and we find that there's a double peak in the histograms, indicating that there's a first order transition into the plaquette VBS phase. And yeah, so we can also look at joint histograms of phi x and phi y. So phi x is on the x-axis, phi y on the right, on the y-axis. And from the positions of the peaks, we can tell that the translational symmetry is broken in both x and y directions, because both phi x and phi y are positive at the same time in a particular configuration. So to conclude, I will just show you the phase diagram. So on the x-axis, I have n. On the y-axis, I have g. And I have not spoken about the low n part of the phase diagram, which also we have studied. But the large n part is much more interesting, where we see a proximate spin liquid at g approximately equal to 0, which eventually goes into a disordered, completely disordered phase, and then transitions into a plaquette VBS phase. With that, I will thank you all for your attention.
Thanks, Nisheeta. Thank you also for sticking to your time. There are questions.
Can you hear me? Yeah. So in equality physics, there is a non-local string order parameter. Like,
Yes.
So is it possible to calculate that with the QMCs?
Yes, it is, but I think the nematic is easier to measure compared to the string order parameter. Yeah, we can in principle measure it, but it's much harder.
Thank you.
Yeah.
If I look at your phase diagram, do I understand it correct that when you increase your system size, somehow that question mark phase disappears?
When I increase the G, this coupling.
No, N.
N. Oh, N is the
N
symmetry.
is okay.
Is a symmetry.
Okay.
Yes.
So you don't see any sign of any deconfined criticality there. It's a it's a superposition of both the states, and then it goes into.
Yes.
Thanks.
Yes.
If you put yourself in the Haldane nematic phase, right? And you do a simulation on a cylinder, right? With just open boundary conditions on one side, and what will happen? Did you try it? You have spin 1/2 chains?
Right. So for if you are able to realize this for a small value of N, you'll get spin 1/2 chains and you get gapless phases at the edges.
But did you check it? Because you have two possibilities. If you put open boundary conditions, then basically the chains could go, if this is periodic here, the chains could go like this and you have nothing, right? Or the chains could go like this, and then you would have a spin 1/2.
Yes. Yes.
My question is, what is more energetically favorable? Do you know that?
What is more energetically favorable in the sense
That if you do it, would you have a spin 1/2 on the open boundary? Will you have a spin 1/2, or will you have some dimerized?
Oh, I see. So right now we are doing this at very large N. So you would see dimers everywhere. But if it was done at lower N, I'm not sure. I'm not sure if it would try to stabilize the gapless phase or the gapped phase. It's not clear to me yet.
Okay, I think we have to move on now. I request the next speaker to come, and let's thank Nisheeta again.